Hello everyone, welcome to part 9 of my probability distribution video series. In this video, we are going to talk about gamma distribution and Erlang distribution. Now, in order to understand this video, you need to definitely go through the past two lectures, which are on Poisson distribution and on exponential distribution. I'm providing you the link in the description. So let's dive in. First of all, gamma distribution is nothing but a general case of exponential distribution. Let me explain what I mean by this. So, gamma distribution is the probability distribution of waiting for time t for r number of events to occur. Now, previously in exponential distribution, we talked about the waiting time for one event to occur, but here that 1 has been replaced by r, and r can be any positive integer like 1, 2, 3, 4, etc. That is why I'm calling this a general case of exponential distribution. Let's say an example. Suppose I get 10 new subscribers per day on average in my YouTube channel. That means lambda is equal to 10 here. What is the probability of getting 5 new subscribers within 2 days? Now this question would actually represent the exponential distribution if we would mention only one new subscriber. But this is now the gamma distribution because we are mentioning 5 new subscribers. That means we are trying to find out the probability of TR, the time for the R events, of being less than or equal to 2 because it is 2 days, where lambda t is equal to 20. So on average, the rate is 10 per day and the rate is 20, 10 into 2 for 2 days. That is why lambda t equal to 20 and the number of events are equal to 5. Now we could obviously solve this if r equal to 1, but we cannot do this now. So let's do one thing. Let's derive the probability density function for this general case when r can be any positive integer like 1, 2, 3, etc. Let's now see how the CDF of gamma distribution looks like. The CDF or cumulative density function is nothing but probability of TR less than equal to T. That means the time for happening R events or R events occurring is less than or equal to T. It's happening within time small t. This is actually equivalent to writing 1 minus probability of R events occurring, which is greater than T. That means within time t, R events did not occur. Let's try to understand probability of TR greater than small t in a bit more detail. What this actually means is that within time t, R events could not occur. That means maybe 0 event occurred, that means no events occurred. Maybe 1 event occurred. Maybe even R minus 1 events are possible within this TR time. But the rth event has to be after time t. So how do we model this? It is very simple. We can model this using the Poisson distribution. So in Poisson distribution, we simply model the probability of some number of events occurring within a fixed time frame. So here, that time frame is t, and we are trying to model the probability of 0 event occurring, 1 event occurring, 2 event occurring up until r minus 1 event occurring. That is why we wrote this as the sum from k equal to 0 to r minus 1. Now understand that this probability of TR less than equal to t, or this function, is a CDF of gamma distribution. So this is just a random PDF curve. You can see that if we want to get the CDF of x less than equal to x prime, then we just need to integrate the PDF curve in this range and we can then get the area. So in order to go from PDF to CDF, we perform integration. Similarly, if we want to go from CDF to PDF, the reverse case, we have to perform derivative with respect to the random variable. That is exactly what we are doing now. We are actually taking the derivative of this CDF function with respect to t, and that is going to give us the PDF or probability density function of the gamma distribution, which looks something like this. So let's look at another real life example. Suppose the expected mutation rate in a cancer driver gene is 3 mutations per year for all the males who are above 50 years of age. Cancer typically onsets when there are 30 mutations or more in this gene. Now, this is just an assumption. There is no relationship with actual medical knowledge with this one. The question is, what is the probability of a man getting cancer before the age of 70? So here, as you can see, lambda is equal to 3, which is the rate parameter, because it is 3 mutations per year. R equal to 30, because we need 30 mutations or 30 events to occur. And this is also known as the shape parameter of the gamma distribution. So we have to determine probability of TR less than or equal to 20, because the mutation started from year 50 and we are talking about year 70. So this whole 30 mutations needs to occur within 20 years of time. So we can easily get this by integrating this function, this PDF function of gamma distribution from 0 to 20. So what is the expected value of this distribution? It is very, very intuitive. It is R by lambda. So previously in exponential distribution, when we were talking about only one event, it was 1 by lambda. So for R events, now it is mathematically been proven that it is R by lambda. Similarly, for variance, it is R by lambda square, and for exponential, it was 1 by lambda square. Now understand that I have conned you a little bit here. I wasn't really honest here. So this was actually Erlang distribution. So, but bear with me. Erlang distribution is nothing but a special case of gamma distribution where the R parameter can only be positive integers. In the actual gamma distribution, the R can be any positive number. It can be 0.55, it can be 1.234, etc. Typically, for gamma distribution, we see some kind of PDF which looks like this. It can actually be obtained very easily from this Erlang distribution by some simple replacement. We simply replace the R with alpha, lambda with beta, and t with x, and that is how we can get this distribution. Here alpha and beta are greater than 0, and x has to be greater than or equal to 0, which represents basically the time. Another thing is, you will typically see gamma of alpha in the denominator. So gamma of alpha is the same as alpha minus 1 factorial, when this factorial can be of any floating point number as well. This is how the PDF function looks like. So for fixed beta, as alpha increases, the curve becomes fatter and fatter. Similarly, if we fix alpha and we keep increasing beta, the curve actually also becomes fatter and fatter, fatter and flatter. So that is all about the gamma distribution. If you like the video, feel free to subscribe and share. There is a link in the description for donation. If you like the video, you can donate to our channel and contribute to our channel. Thank you very much.